Okay, let's see. Some of you were at the colloquium last week, physics department colloquium. Raise your hand if you saw the colloquium. Okay. So the speaker was from IBM, and he was talking about applications for the photoelectric effect. And, it was pretty technical, I thought, even though he tried to make it accessible to students. I thought it was pretty technical the whole time. But he drew a diagram, so let me tell you, so for those who were there, I'll help you to try to get a little bit more out of it. He drew a diagram. This is supposed to be the surface of a metal, but now this is an energy diagram. So in the vertical direction is energy. And he had something like this. A diagram like this. So this is supposed to be outside of the metal, and this is supposed to be inside of the metal. And the idea of the metal is that you have something, say, a centimeter across. You have a particle in a box. Only a lot of particles, right? You've got a lot of electrons. And the box is three-dimensional, so it's a cube. So we could study the solutions to Schrodinger's equation for an electron inside of this cube, and it would be very similar to what you saw for one dimension. And it's just a three-dimensional version of that. So there is a sequence of energies. But remember those energies for the particles, the particle in a box, the energies went like 1 over the square of the size of the box. And there's a similar sort of thing in 3 dimensions. So if the box is on the size of a centimeter, well, let's start off with the box is on the size of a hydrogen atom. These energies are like electron volts. And if you're talking about a centimeter, that's orders of magnitude bigger. And it's squared. So the spacing between the energy levels is very small. And so he draws, most people draw it as a continuum of energy levels. Yes, ma'am.
So it's squared if it's on the level of a centimeter, but if it's on the level of a hydrogen atom, it's not squared?
No, it is
squared all around. Oh, okay.
No, I mean, the fact you're going from a hydrogen atom to a little box on the size of a centimeter.
Oh, okay.
Several orders of magnitude squared, right? Scales with size squared.
Thank you.
Okay, now the other factor that we're going to talk about later in this course, you may have heard this. We've been only doing one electron at a time. We've been doing an ensemble of systems, but each system has only one particle, right? So now we're going to be faced with the fact that we've got a lot of electrons in this little cube. And the electrons will not occupy the same state. And so when we're looking at the particle in a box, let's put 2 electrons in. And then we have this sequence of energy levels reaching up to infinity, going like n squared. Particle in a box. And so the spacing between these energies is increasing. If we put in 1 electron and then another electron, it cannot occupy the same state. So it has to find another state. Now there's a complication having to do with spin I don't want to talk about right now, but in principle, you can't put 2 electrons in the same state. So the next one would have to be here. So you have to add additional particles into the box. Now you're get the lowest energy, you still have to pile these particles up. And that's what this hatching here is supposed to represent. A lot of electrons that are piled up to the highest level, which is called the Fermi level. Fermi energy or Fermi level. Okay, and then he was talking about taking an ultraviolet source, pretty high frequency, bluer, past the blue end of the spectrum, so it's high frequency. And then exposing the metal to that, and then ejecting electrons, which means that you have to get them over this energy barrier. Remember, we talked about the work function. So the energy of the light has to be greater than this work function. So you're taking, if the energy is less, there are no electrons that are close enough to this free state. And so you have to get the energy of the light above this threshold, and then you can now start pulling electrons, taking them out of the metal. And then you can analyze the energy of those electrons. That's the spectrum that we show. So it's called ultraviolet photo emission process. It's UPS. And he did all kinds of variations and refinements on this. But this is the basic idea. He was able to show how you could study interfaces even in microelectronic devices and study the details of how these transistors and diodes and things perform using this photo emission. He also mentioned the word, maybe you noticed this, he said it a few times, K-vector. What's the K-vector? Well, it's the three-dimensional version of the wave number. And so it's a vector. So the proportionality is h bar, so the momentum of an electron is proportional to the wave number, which is a three-dimensional. The proportionality is constant. So he said that several times without explaining it. So maybe you picked up on what that was. Okay, so I hope that helps explain a little bit of what you were watching. Pretty cool application of the photoelectric protection. So, yeah, how's it going?
Oil fell into the speaker area.
Yeah. Next up,
it's not. Yeah, next up.
I thought that might happen.
So we'll have to get a new one. That's.
I think it's laying down. I think it's actually laying down up here. Because you can, if you turn it on, you can actually feel the finger on the actual. Feel vibrations going on right here. Yeah. The problem is that everything itself is like this extra weight.
Magnet's fine. Just the.
Oh, that's too bad. We had a cool demonstration, but maybe we'll be able to get it.
Some of the coolest experiments ever.
Yeah, it really is.
Yeah, we'll try to get it up again. Just a Uber. They just have to get a new one. So
okay.
We'll do that again.
All right.
I'll come back and collect this.
Thank you for trying.
No problem.
Okay, that's too bad. We'll save this for another day. I'm going to talk about the bouncing droplets. That's the experiment, which is really cool. So we'll save this for another day.
Oh, yeah, not doors.
Okay.
That's the door oiled up. Yeah, he's all oiled up himself.
Yeah, silicone oil.
So I'll give you the full story about this on another date when we have the demonstration. It's really cool. Okay, so we're talking about Fourier transforms. And we introduced the idea of having a transform using the wave function. Maybe a little bit more. Raise the camera a little bit because we don't have the demo. Okay, so psi of x is formed as a superposition. Plane waves, and I think he follows the convention factor 1 over √2 pi here in the Fourier transform. And then you can go in the opposite direction from psi of x. You can find the phi of k by doing an integral over x. Okay, so don't get confused by this. Remember here, k is a dummy index that ranges. It's a real number that ranges from -infinity to +infinity. You're adding up a bunch of an infinite number of contributions at x. And this on the right-hand side, the integral depends, the function of x. The integral, the value of the integral depends on x. This is a function of x. Now in this one, we have the complementary situation. X is now the dummy index that's running from -infinity to +infinity. You're adding all of these up. And so integrating over x, but now k is a fixed value. So this integral depends on k. And phi of k is a function of k. And so you can go back and forth from psi of x to phi of k. So this has been the Fourier transform of the wave function. And so let's look at an example. We had a Gaussian wave function. This is from the book 142. Wave function is square root of sigma naught minus x squared over 4, right? Or sigma naught squared. This was the wave function at time 0. So we'll just call that full psi of x. Okay, so it's a function of x. And so let's study this. This is not the probability, this is the probability amplitude. To get the probability, what do we do?
Phi star psi.
Phi star psi. This happens to be real here, so sigma naught is real. Yes. Okay. And so if we calculate the probability, we take psi star psi. So that's up times 0. This wave function is real everywhere. There's nothing but real parameters in here, real numbers. And so we just take the square. Okay, so this is the probability. It should be, if you integrate this, over all values of x, what you get? You get 1, right? So probability 1, because probability is a fraction. It's the number of members of the ensemble that show up in that interval. Don't show up with a value around x. Okay, so let's look at this a little bit. What is the dimensionality of x? X is a length. So what is the dimensionality of sigma naught? Actually, it has to be a length also, right? Because it has to be x squared over sigma naught squared has to be dimensionless. So sigma naught also has to be a length. Okay, and then we check the probability here. Right? The probability density. I should call it probability density. Has to add up to 1. So I'm going to multiply it by a length here. So what is the dimensionality of the probability density? Inverse. Here we have an inverse length. Yes, ma'am.
My math is getting wrong in my head. How did we get the 2 pi squared? Should it be 2 pi to 1/2?
Yeah, thank you.
Okay.
1/2. Was it your head? Mine.
I never know if it is.
Thank you. Okay, so you should be able to look up this integral in a table of integrals. The table of integrals that is provided on Canvas is one of these. Has this entry in it and confirm that you get 1. Okay, so let's do the Fourier transform. This function. We get a phi of k. And it's going to be the Fourier transform of this. So we substitute this into here. Okay, so we got all these constants. I'm not going to worry about these constants. You're going to do this for homework. I'm going to let you keep track of the constants. The essential part that we're concerned about right now is this. Okay, so again, that's an integral lookup. You can look up in the Fourier table of Fourier transforms. You're transforming this, and it may be in the table Fourier transforms. It may be doing something like this: e to the minus alpha x squared. You have to figure out how does alpha relate to sigma naught. So when you do the transform, going to come up with something that looks like, I'm not sure that it's 4 here. I'm not sure exactly what the factor is, but you're going to transform a Gaussian in X, transforms to a Gaussian in K. This is the result of doing the interval. If you would like the challenge, you could confirm this entry in the Fourier table. I'll give you extra credit for doing that. I'll give you a hint to do that. This is, you combine these two exponentials, it's a quadratic polynomial. Complete square, you can pull out this. So it's pretty simple, actually. Good at redefining variables, completing squares. Okay, so we have, and notice here, this is important. What is the dimensionality of K? Dimensionality of the wavelength. Various places you can get it. Remember first, what is the definition of K? Pi over the wavelength, the Broglie wavelength. So it's a 1 over length. But there's other places you should find that. That has to be dimensionless. So K has to be the inverse of dimension of X. And here, this thing should be dimensionless. Sigma naught, we said, is a length. So K has to be an inverse length. So that sigma naught squared, K squared. Okay. So that's an example. 2 or 3 that you're working for homework. I think there's a couple of challenge problems as well. And then the one I just mentioned, I'll add just to do this integral yourself, confirm the entry of the paper. Okay. Any questions about that? I'm about to talk about the meaning of 5K. The information content that we have here corresponding to experiments. But if you have any question about this. Okay. All right, so we had down this relationship between psi star psi, and what is the name of this rule? Rule. What's the name of the rule? Born rule. Yeah. Named after Max Born. Anybody here know Olivia Newton-John, or is that too far past?
I've heard it.
She was Max Born's granddaughter.
Yeah. Oh.
She was like a music.
Yeah, she was a singer, entertainer, actress. But it's been a while. Okay, so Max Born, that's the Born rule. And then we just saw through, if we can go from here using the Fourier transform, something that I'm going to call I'm going to use capital phi to denote the Fourier transform of capital psi, and then there's a lowercase, right? If there is something like a lowercase wave function, then there's a lowercase phi that goes with that Fourier transform. But this way or that way, either way, right? It's just the same thing as the inverse Fourier transform. So we should know how to do this. What is the meaning of this thing? In other words, this was a function of x and t. What could that be? What was k again? What's the relation of k? I always said the de Broglie wavelength 2 pi over the de Broglie wavelength, but there was the de Broglie relation. What was the de Broglie relation back in chapter 1?
So the moment the h over lambda,
right? Remember that? Okay, now I'm going to put in a couple of factors of 2. it seems silly to do it here, but there's a reason for doing it at other places. It makes things more convenient not to have vector systems floating around. This is H bar. And this is K. So another way of writing the de Broglie relation, and I know I'm not pronouncing de Broglie correctly. Another way of writing it is this. Okay, so K is proportional to the momentum. And people, in fact, just talk about K vectors, meaning momentum. Okay, let's go back to this. K is related to the momentum. So I could measure the position, and remember the Born rule is the probability density. So P of X dx. Probability of finding the particle in a interval of this width dx centered around X. Any thoughts about what this might be?
We're not talking about lowercase phi. We're doing Fourier transform with that. We're doing Fourier transform the wave function.
The only difference was the time dependence, right? Whether it's time dependent or not. Yeah. So
would it be the probability of a particle having a certain momentum at a
bingo.
given time?
Actually, wave number. Wave, right? So let's call this Q of K of T. So Q, K, T, K. The probability density, oops, just Q of K is a probability density, but again, we're using density now. The interval is over K. So in other words, Q of K of T, K. The probability of finding, in other words, it's the fraction of the ensemble that shows up at K, between K and K plus TK. The wave number in that interval. In other words, just multiply by H bar to get the momentum. You do enough quantum mechanics, you choose a system of units where H bar is 1, so you don't have to write it down anymore. So you try to calculate it in a more common system of units. So people just stop talking about the K and P as being different from each other. So this is the probability of finding particle between X and X plus dx. So with that position, this is the probability of finding a particle with that momentum. Yes, sir.
So for the Q and phi, does that rely on the particles being different, or the because for an atom, for instance, aren't all the particles trying to get the same speed?
No. Yeah. Okay. So, all right. So let's remind ourselves. Go back to this. The average position, for example, but there's going to be a distribution in position, even for energy. If I measure the energy, there's going to be a distribution in energy because of the stochastic part of the guiding wave structure. It's hitting the particle, knocking it around. So if I look at one particular system, it's not going to be right at the ground state energy. It's spread. Distribution of energy. Same is going to be true for K. It's going to be a distribution of K. And you can find that distribution by doing the Fourier transform. So I could put a particle in a box, or I could put a particle in a Gaussian. Fourier transform of a Gaussian is a Gaussian. So I would have a Gaussian probability distribution of X, and I would have a Gaussian probability distribution of Y. It doesn't have to be that way. That's a very symmetrical thing. So you could have it, obviously, in other words, the wave function is not going to have the same functional form for both waves. This happens with Gaussian, but Gaussian transforms from Gaussian, not generally. Did I answer your question?
Yes.
All right, so what is the dimensionality of Q? Q dk, I have to integrate Q dk. If I integrate over all values of k, from minus infinity to plus infinity, what do I get? Get 1. What does that say about the dimensionality of Q?
It must be L.
Yeah, 1 over k,
Yeah.
which is itself 1 over L. It has to have a dimensionality of L. Probability density in X has a dimensionality of inverse L. Q has dimensionality of L. But you're going to integrate this over X, get 1, and integrate this over K, get 1s. Okay, so far? Okay, so we also found that if we multiply the probability density by X, integrate over X, we get the average, the ensemble average. Remember how that works. I make 1 million copies of the system, starting off in some wave function. Everybody's got the same state. One part. Make 1 million copies and hand it out to 1 million people. Everybody waits a certain time. Everybody's got to wait the same time. Then make a measurement and report back X. So there's a distribution, make a histogram of all the reports coming back. This is maybe the average of all. And also, average of X squared gives you the average of the square of all the values. And why do we do that? Because this can be formed into the uncertainty. Statistical uncertainty for the ensemble. That. Remember? Got a new probability density. K space. Called K space. Momentum measurement. So we're going to measure momentum. Okay, prepare the state in this, prepare a system in this state, I make 1 million copies of it, I hand them all out. Everybody measure momentum this time. I'm not going to explain how you're going to measure the momentum, but everybody's going to do the same measure. Everybody gets a definite value of the momentum. There's no uncertainty in your measurement, your individual measurement. So we bring back all the results and we make a histogram of these measurements. And then we take the average. In other words, you just take the average of all the measurements coming back. I'm going to do it in terms of, well, let's do it in terms of P, sure. Just, of course, the average of K. Multiply by 8. Very similar. So the meaning of this is everybody tells me value, gain, take the average. Maybe nobody got that average. Remember, there might be nobody at the average. That is mine. Sometimes my K, if I write it too fast, looks like an H. I think that better. Okay, and then uncertainty. Where's the uncertainty? Talk about the uncertainty here and also the uncertainty in X. Uncertainty in momentum, uncertainty in X. What does that mean, uncertainty?
It's not just how it relates to the average, how that particular measure relates to the whole. Probably held up for the sample on that particular measurement that one guy writes to the average of the ensemble.
What about a particular measure? You're on the right track. It's ensemble. The spread of the ensemble of the measurement. Not about any particular one. It's about how does the ensemble, how is the measurements distributed among the members of the ensemble. So you could have, for example, over here maybe a Gaussian. Doesn't have to be a Gaussian. I'm just going to draw a Gaussian. Gaussian probability distribution. If it's Gaussian, it's very convenient. The width of the Gaussian is sigma, right? Standard deviation of the measurements. And the height goes like 1 over sigma. If it's a Gaussian wave function, then you'll get a Gaussian probability. You also get a Gaussian in K as well. There will be a Gaussian here as well. And then the width here corresponds to the width of the measurements of the momentum. So there's a distribution here. So P of X. Q of K. Sigma K, right, is just a factor H part. Okay, now it happens for a Gaussian, the Gaussian becomes a Gaussian. But there are other probability distributions. I'm writing a really simple example here, and I don't want you to think they're all probability distributions or bell curves. They're not. Lots of possibilities. So maybe, in fact, just to drive home that point, let's take some other example. Remember the plane wave. Delta function. Okay. Right? This plane wave had a uniform probability. Uniform everything. Same probability of finding the particle anywhere. But the momentum distribution is a delta function, P. So P of X is a uniform thing over here. Over here. Delta function, like that. Trying to think. Okay. I'm trying to think of something that's not a Gaussian. We're going to end up doing Gaussians because they're so simple mathematically. I just want you to realize that in general, probability distributions are not Gaussians. You could have, for example, I remember. We did right and left traveling plate that had 2 delta functions. Okay, so minus K plus K. Here's the average. K. 0. There's nobody there at the average. What's the width? K squared. Right, the average of the K, half of them are plus K, half of them are minus K. You square both of them. K squared minus K squared. The average of K squared is K squared. See how that works? Average of K squared, K squared. Yeah. In this case. I guess I should do it this way. Make it a little clearer. There's a capital K. Distinguish it from variable K. So this is Q of K. You cut out the delta function, right? Plus capital K and minus capital K. The average of K here is 0. The average of K squared is big K squared. How that works? Have to be careful of the symbols here. Okay, so yes, ma'am.
So X represents position. So like all of these values are like the average of the position.
Yeah.
And the exact same thing is true for the P values, which is momentum.
Correct.
So everything that X is in position, P is in momentum.
Yes.
Okay. Thank you.
Now we're going to find that there's an interesting relationship between the uncertainty in X and the uncertainty in P. The uncertainty has to do with the ensemble distribution. Somebody says, wait a minute, I did a measurement. It was over here, right? It's away from the average. Doesn't matter. This represents everybody pooling the results together. Individually, the individual measurement, they have no uncertainty. Uncertainty doesn't correspond to experimental uncertainty of your measurements. it corresponds to the width of the distribution when you pool everybody's results. So it's a standard deviation of the measured values. Each measurement has no uncertainty. Does that make sense? Okay. So now let's do something. We're going to start psi of x, and t represents the wave function corresponding to an ensemble. It's got one particle in each copy. Hand it out to everybody. We got 1 million. Let's make 2 million. It's going to be safe. Make 2 million copies. We got 2 million people. Going to make a measurement, but hang on. I'm going to divide it in half. I'm going to make 2 sub-ensembles. This ensemble is going to measure X. This sub-ensemble is going to measure P. On no system are 2 measurements being made. That's very important to remember. Nobody's making 2 measurements. You're either in the X sub-ensemble, in which case you're going to measure X, or you're in the other half, which is called the P sub-ensemble. You're going to make a measurement of P. Okay? And those 2 are kept separate from each other. And on no occasion does anybody make 2 measurements. Okay, so you go through this process. Average x squared, find the standard deviation. So we get an uncertainty in x. Corresponds to an uncertainty within the ensemble. Not uncertainty in anybody's measure. Same thing here. Get a bunch of measurements p, average them, average the squares, get a standard deviation. The canard uncertainty principle is that no matter psi of x, psi is a lower bound. In general, it's above h bar over 2. If psi of x at t is Gaussian, it's equal to h bar over 2. That's the case where it matches the lower bound. In general, it's more. So if regardless of what psi is, there's a floor on this product. So that means if I prepare this ensemble here so that it has a narrow distribution in x, that means the corresponding other sub-ensemble is going to have a y distribution. Okay. That means to make something that's localized, make a wave function which is tight, some confined region, I have to involve a big spread of momentum. Why is that? Remember the relationship between momentum and the de Broglie wavelength. Get something confined with a small confinement. You have to have a big spread of wave function, of wavelengths to get that type confinement. You have to have a superposition of wavelengths to make it confined. That superposition of wavelengths shows up as a spread in P. So there's no way to confine it without spreading the uncertainty in momentum. That's ensemble uncertainty, right? It's that the wave function has contributions in wavelength from a big variety to get it tightly confined. Yes?
Is with the uncertainty principle, is it kind of saying that when you have more information of one, you're more certain of another?
No. Yeah, that's exactly what it doesn't say. And that's what I'm trying to get out of your head. You've heard that. That's not correct. So if this was also, Heisenberg originally discussed something else, which is similar, but not the same. Heisenberg noticed that if I try to measure the position of a particle, I disturb it. So if I were to make a measurement afterwards, another measurement, the second measurement will be altered by the first. That's simply a statement that making the measurement on the system disturbs the system. So that's called a disturbance relation. Heisenberg wrote this, but that wasn't what he was talking about when he wrote this. And people get the two things confused. Okay, so there is an uncertainty principle called the Heisenberg uncertainty principle, which has been badly explained. People write this equation and call it the Heisenberg uncertainty principle. And they'll say some words about like what you just said. That's why I'm going so slow to explain this point so carefully to you. The Canard uncertainty principle, this equation, means exactly what I just said. Divide the ensemble in two, and on one side you measure x, on the other side you measure t. On no case, on no occasion is anybody doing two measurements on the same system. Okay. Now there's another relationship which we should call the Heisenberg uncertainty principle, and which you'll talk about in the book, which we'll go over some. And that has to do with successive measurements. Two measurements on the same system. And the fact that one measurement will disturb the system, change the wave function as a result of the measurement, and thereby alter the expected value of the second measurement. Okay, so that's common. So what's called the Heisenberg uncertainty principle. Not that. And in fact, a better name for it now, a lot of work has been done on this. See, it's called the measurement. See, disturbance. I forgot the name of it now. The measurement disturbance relation. So Ozawa was working, this is actually recent work. When I was a graduate student, I started hearing about the LIGO experiment. And the precision behind that measurement in order to determine the presence of gravitational waves is really challenging experimentally. They were pushing what's known as the quantum limit of detection. And so all of this became important again. How far can we go in measuring gravitational waves? So Ozawa was working on that problem. Realized that there was a lot of confusion in what was called the Heisenberg uncertainty principle. Okay, so that's mentioned in the book. This takes a while to go through, so we're not going to go into it in detail. But I do want you to remember that this, what the meaning of this is. Even though it will be called the Heisenberg uncertainty principle, it's not the way people explain it. So it's important to know this distinction. Yes, sir.
The Canard and Heisenberg are two different uncertainty principles.
Yes.
And we're going to cover Heisenberg soon.
Yeah, briefly.
And Canard is saying, why do we have to break it up? Why do we have to break it up into two subatoms? Why do we have to do that?
You don't have to. But it is a statement of what happens if you do.
Because I understand
to do the Canard uncertainty principle, you can't make two measurements on the same system. Each state is being met, each system is being measured once. It's a question of what you're measuring. There's a complementarity between measurements of X and measurements of T. That's what that's showing. But not done at the same time, or not done on the same system, right? Each person receives a copy and makes a measurement of either X or T according to instruction.
Oh, so you have like 50 people, they'll measure.
Yeah.
They'll measure their own. So everyone's got their own, let's say you have 100 people, you got their own box.
Yep.
So 50 people at their own box, they're going to measure X, and 50 of the other people, their own box, are going to measure momentum.
Yes.
And then those are two up. Okay, that's pretty cool. Okay,
Yeah.
that makes sense.
That's why I started with 2 million, right? 1 million and 1 million. You need more probably than 50 because there's some statistical, there's noise in the ensemble, noise in the sense of you're going to be sampling some probability distribution. You probably need more than 50 to get a good idea of what the average should be.
How do they get H bar over to that's just from from them measuring it, they notice that, or like?
No, there's an argument from the Fourier transform. So you can actually remember we can get this by doing a Fourier transform. So this is actually a property of Fourier transforms. So you can actually prove this from the Fourier transform relation. That you would get to get the Fourier transform on the wave function, and then you perform the averages, as I said, on that Fourier transform. So this is actually, if you work with just X, I'm sorry, just work with K, take the H bar out, then it's a relationship between the position uncertainty and the wave number uncertainty.
How big is it?
I'd have to show you, this is a theorem that comes from Fourier transforms.
Okay.
He shows you in the book, in order to confine the particle to a narrow region, you have to have lots of wave numbers to accomplish that. It's the same thing that happens in sound. To have a short sound that takes place over a second, you have to have a lot of frequencies contributing in order to make the sound go away outside of that 1 second. So that the frequency analysis of a short sound show a broad spectrum of frequencies. A narrow spectrum in frequency would correspond to a long sound. That's what this is. There's an analog to that. Analog relation between X and K. Remember, K is like a spatial frequency. Okay, so we'll do more on this. Be more discussion. All righty, so I have to head out today. So I'm ending a couple minutes early. Are there any questions before I let you go?